Ever stop and think about how your computer manages to do billions of things at once without just melting down into chaos? I mean, it feels pretty seamless, right? But inside its core, it's this wild ballet of coordination. Today, we're going to pull back the curtain on the design principles of the one component that makes it all happen, the brain of your computer's brain. Because really, that's exactly what it is, a beautifully controlled chaos. You might picture the inside of a CPU like a neat, orderly factory. But a better way to think about it is a stage, and it's filled with some of the most talented, specialized performers you can imagine. The catch? Without a director, all you've got is noise. That's right, we're going with an orchestra analogy here, and it fits perfectly. Each little component inside that chip is a virtuoso, capable of doing incredible things. But if they all just do their own thing at the same time, well, that's not a symphony, it's a disaster. They need a conductor. All right, so here's our roadmap. We're going to start by meeting this chaotic orchestra. Then we'll see the conductors step up to the podium. After that, we'll look at two totally different conducting styles and get into the huge trade-off between speed and flexibility. And finally, we'll see why the conductor's choice here matters in pretty much every device you've ever touched. Okay, first up, let's actually meet these performers. These are the fundamental building blocks of how a computer thinks, and each one has a very specific and very powerful job to do. So you've got a few key players here. There's the math whiz, the arithmetic logic unit, or ALU. It handles all the heavy calculations. Then you've got these lightning-fast scribes called registers, which hold tiny bits of data right where you need them for the very next action. And of course, you have the orchestra's entire music library, the main memory, or RAM, which holds all the programs and data. They're all brilliant, they're all ready to go, but they're just standing there, waiting. Not a single one of them knows when it's their turn to act. And that's our cue. It's time for the conductor to take the stage. To bring order to all this brilliant chaos, computer architects came up with a really elegant solution to lead this digital orchestra. And this is it, the control unit. Now, its job isn't to do the math or to hold the data. Nope, its job is to direct everything else. It reads the sheet music, which is your program's instructions, and it points to each section of the orchestra, telling it exactly when to play, what to play, and where to get its notes from. And the rhythm this conductor keeps is surprisingly simple, but it is absolutely relentless. It's a 4-step beat. Fetch, decode, execute, repeat. But get this isn't happening a few times a second. It's happening billions of times every single second. It's just incredible.
Okay, but this is where it gets really, really interesting. As it turns out, not all conductors work the same way. When you're designing a CPU, there are two fundamentally different philosophies for how to build this control unit.
On one hand, you have the strict conductor. This is the hardwired design. Think of its logic as being physically etched right into the silicon. This makes it insanely fast. There's no hesitation. But it's completely rigid. If the music changes, you need a whole new conductor. On the other hand, you've got the interpretive conductor, or the microprogram design. This one reads its instructions from a special little rulebook called microcode. This makes it way more flexible. You can even update the rulebook later. But it's a little bit slower because it has to take that extra step to look up the rules. And right there, that's it. That's the core challenge, the fundamental trade-off in pretty much all of CPU architecture. Do you build for pure, raw, unadulterated speed? Or do you build for adaptability, for the ability to handle more complex and changing instructions? And believe me, this isn't just some minor engineering detail. This one choice shapes the entire personality of a processor. It decides whether the orchestra is built for a lightning-fast sprint playing one simple song, or if it's a versatile symphony that can play just about anything you put in front of it. Let's just break it down really quick. For speed, hardwired wins, hands down. It is just faster. But for flexibility, oh, that's microprogrammed all day long. Now look at complexity. That hardwired design is incredibly complicated to get right from the start. Microprogrammed is actually easier to design and to fix. And finally, cost. Hardwired is cheaper to mass produce once the design is locked in, but microprogrammed can be more expensive per chip. See, there's no single best answer. It's all about what that final performance is supposed to be. So, okay, why should you care about any of this? Well, because the results of this single design decision are in every single piece of technology you use, every single day. This choice has a huge real-world impact. That strict hardwired approach, that's the heart of RISC processors. That stands for Reduced Instruction Set Computer. Think of the chip in your smartphone.
It's built to do a smaller number of things, but to do them incredibly fast and efficiently. The more interpretive, micro-programmed approach, that's the basis for CISC, or Complex Instruction Set Computer Processors. These are the workhorses in our laptops and desktops, built to handle all kinds of complex symphonies. That simple chip in your microwave? That's a strict hardwired conductor. And the ability to update your computer's most basic functions with a software patch? Yeah, you can thank the flexibility of a micro-programmed conductor for that.
So if there's one thing to take away, it's this. The design of that central conductor, whether it's a strict traditionalist or a flexible interpreter, it doesn't just change one little component. It defines the capability, the speed, the entire nature of the whole computer system. It dictates exactly what kind of symphony that machine was built to play.
And that leaves us with a really big final thought. You know, the symphonies our computers are being asked to play are changing. With the rise of AI, tasks are becoming less about rigid step-by-step calculations and way more about pattern recognition and learning. So the question is, will the conductors we have today be able to lead the orchestra of tomorrow? Or are we going to need to invent a completely new style of conducting altogether?